Welcome to GATE Academy. So, in this lecture we will discuss some fundamental concepts from the subject of strength of material which are very essential before starting the subject of machine design, okay, and these concepts will be very helpful in the topic of theory of failure, okay. So, let us start with the basics for the subject from strength of material, okay. So, if we talk about the subject strength of material, then in this subject we majorly deal with stress and strain, okay. We majorly deal with stress and strain. I will be telling you what is stress, what is strain, okay. And here the strength of a material is nothing but the value of stress which the material can carry without failure, okay. So, strength is nothing but the maximum stress which a component can carry without failure is known as the strength of material, okay. So, different materials will be having different strength. Now, the concept of stress is very simple. It is the resisting load per unit area, okay. I will be just dealing everything in brief, okay. We won't go in details as this is just a recap of the subject of strength of material, okay. So, stress is nothing but resisting force per unit area, Now, what is this resisting force? If any component is subjected to an external load, let us consider a component of length L and having a cross section area A, and it is subjected to a load, external load like this, then this load will try to deform this particular member, okay. As the fundamental nature of a force is to change the state of motion or to change the shape or size of any material. This is the fundamental nature of a force. So, this is a force. So, being a force, it will try to change the shape of this member. Now, the member will try to retain its shape, it will try to maintain its shape, it will try to remain its initial shape and size, okay. Hence, it will produce some resisting forces so that the effect of the external force can be encountered, okay. Hence, the internal forces will be produced in the material, and this is because of the intermolecular attraction force between the molecules of the member, okay. So, if you want to analyze that what is the magnitude of the resisting force, then we will be using this method of section, okay, So, we will use the method of section, for analyzing internal forces, okay. Example is the resisting force, okay, okay. So, cut a section at any location, let us say XX is a section located at a distance of x from the right hand, then you can see that this is the external force, this is this section XX, and here we will be having the resisting force F, okay, the resisting force F. Now, basically here I have considered the sum of the resisting force offered by each and every particle, okay. So, this is the total resisting force, okay. Now, as in practical application the forces offered by the particles present at different location may vary, hence the force will be distributed over the cross section, okay, and I am summing up all the forces and I am getting the total resisting force, okay. Now, the stress is resisting force per unit area and the cross section area is A. So, stress will be equal to F by A. Now here for condition of static equilibrium, the summation of all the forces must be equal to 0. Okay, so here also this forces should maintain the static equilibrium, hence this will be P minus F is equal to 0. So P is coming out to be F. So for condition of static equilibrium, the internal resisting force or the resisting force will be equal to the external force. Okay, so hence we can write it as P by A, Now P has a unit of Newton and the units of area is meter square. So Newton per meter square or Pascals is the standard unit for stress. Okay, so this is stress. Now as I have told you that if a component is subjected to an external load, then the fundamental nature of the load, that is a force, is to deform the body, that means to change the shape and size of the body, hence there will be a deformation as well. So along with stress there will also be a deformation. Now we will be measuring the deformation in terms of strain. Now what is strain? Strain is deformation per unit original dimension. Okay, so strain is equal to deformation divided by the original dimension, or you can also write it like this, that is change in dimension divided by the original dimensions. Okay, divided by the original dimension. So this is the fundamental definition of the strain. Okay. Now according to different types of stresses, there will be different types of strain. So the basic definition of stress is resisting force per unit area. So you can write stress is equal to resisting force per unit area. So resisting force divided by area. Okay, this will be the fundamental relationship for the stress. Okay, this stress is a certain kind of stress. So we have taken a certain kind of loading, for example, hence I am getting a certain type of stress. So there are several types of stresses. Okay, so stress can be categorized as normal stress, and shear stress. Okay, so the normal stress is the stress acting in a direction normal to a plane. So if there is a plane in the body which is being loaded like this, so let us say here is a plane. Okay, so the stress acting in a direction normal to this plane will be known as normal stress, and it is represented by sigma n. Sometimes it is also represented as sigma theta, because it is acting on a plane which is inclined at a certain angle, okay, which is theta. So the normal stress can be denoted by sigma n or sigma theta. So it is nothing but the stress acting in a direction normal to a plane. Now sometimes there is another kind of stress, that is the longitudinal stress, is used to analyze a situation. Now what is longitudinal stress? Longitudinal stress is nothing but a kind of normal stress. It is a kind of normal stress. So in this category you will also see longitudinal stress. Okay. So what is longitudinal stress? Now if you have a body like this, let us take a rod for example. Okay. Now the dimension along which the rod is longest, or any object is longest, like this pen is longest about this direction. Okay. So the dimension along which the body is longest, that is having largest length, that dimension is known as longitudinal dimension, and the axis along that dimension will be the longitudinal axis. So this will be the longitudinal axis. Okay, and after that there will be two more axes, and they will be perpendicular to the longitudinal axis. So there will be basically 3 mutually perpendicular axes. So remaining 2 axes will be known as the transverse or lateral axis. Transverse or lateral axis. Okay. Now, if the load is acting along the longitudinal direction, then the stress will be produced on the cross sectional area of the rod, okay, and that stress is known as the longitudinal stress. So, normal stress is nothing but a stress at the cross section area, okay. So, the longitudinal stress is nothing but a normal stress at the cross sectional area. This is normal stress at cross sectional area, okay. So, the normal stress will be acting along the longitudinal axis basically, because it is normal to the cross section, this will be the cross section, and it is acting perpendicular to the cross section, that is normal to the cross section, hence it will be acting along the longitudinal axis. So, in this case the sigma n will be acting along the longitudinal axis, and here the stress is represented by sigma. So, basically a longitudinal stress is represented by sigma, okay. So, this example belongs to longitudinal stress, longitudinal stress, okay. Now shear stress. So, if there is an external load which is acting in this direction, then at any plane you can see that there will be 2 component of the forces. One component of force will be normal to the plane, which will be causing the normal stress, and another will be parallel, that means tangential to the plane, and that will be causing shear stress, okay. So, shear stress will take place if 2 planes are trying to move relative with respect to each other, okay. Then there will be a tendency in the material to stop this relative motion, and hence a resisting force will set up, and due to this resisting force there will be a shear stress. So, shear stress is shear force or resisting shear force per unit area, okay. So, what is shear force? Shear force is non-collinear parallel force, So, let us say that it is a plane, this is a plane, okay, and this is another plane. Now, here you have applied a force, okay, and due to this force, this plane is trying to move relative to this plane. Now, as these planes belongs to a body, so the body will be trying to resist this force, and in order to resist this force, equal and opposite force has to be applied. So, a resisting force will set up, okay, and this resisting force will be there just because of the molecular attraction, and this resisting force is the shear force, okay. As there is relative motion between the planes parallel to each other, hence there will be a shearing action, that means this particular plane will try to separate from this adjacent plane, okay. So, this is shear force per unit, resisting shear force per unit area is shear stress, okay. Shear stress is represented by tau, So, tau will be equal to V by A. V is the shear force, A is the area under shear, okay. Now, according to these stresses, there will be different types of strains, okay. So, corresponding to normal stress, here we will be having normal strain, okay. So, it is represented by epsilon n, and it will be the change in dimension along the normal direction and the original direction, okay. There will be having longitudinal stress. So, corresponding to the longitudinal stress, we will have longitudinal strain, Okay, epsilon, simply epsilon or epsilon L you can say. So this will be change in length divided by the original length, original length. Okay, and when a component is subjected to any stress, okay, then there will be change in their lateral dimension also. Okay, so here we will be having lateral strain also. Okay, lateral strain, and lateral strain represents the Poisson's effect. Poisson effects mean if there is extension in a rod, then the length will increase but the cross section will decrease, and if there is a compression in the rod, then the length may decrease and the cross section will increase. So I will be telling you the Poisson's effect, but let us see lateral strain. So lateral strain is the change in diameter divided by original diameter. Okay, or you can write change in lateral dimension, change in lateral dimensions divided by the original lateral dimension. Okay, original lateral dimension. So in case of a cylindrical rod, you will be having the diameter. In case of a square cross section rod, okay, or a square bar, you will be having the height, the side of the square as your lateral dimension. Okay, if this is a bar having a square cross section, then you will be having the side of the square A as your lateral dimension. If there is a rectangular bar, then the width and the height will be the lateral dimensions. Okay. Now, corresponding to the shear stress, we will have shear strain. Now, shear strain can be represented by phi, or you can also write it as gamma. Okay, as gamma. Now it is very easy to understand. If you have a element like this, now it is fixed at this end, that means here you will be having a resisting force like this, okay. If you will fix it, then definitely you will be having a resisting force. I have removed the support and I am representing the resisting force V. Okay, here is the applied shear force. Now due to this shear force, all the fibers will try to move relative with respect to each other like this. Okay, hence there will be a tilting of the square shape by some angle, and that angle is, let us say, phi. Okay, let us say this side is L, and the axial travel of the point A up to A dash is equal to del L. Then this angle phi, which is very small, so phi being very small, tan phi will be equal to phi, hence shear strain phi can be written as tan phi can be written as del L by L, or as tan phi is equal to phi. So phi will be equal to del L by L. Okay, so this will be the shear strain. Now there are some different types of strains as well, like volumetric strain is also there. So volumetric strain epsilon V is equal to change in volume divided by original volume. Okay. So these are the different types of stresses and strain. Now there are some constitutive equations and there are some fundamental laws which will be defining the relationship between the stress and strain, and the constitutive law for any solid is Hooke's law. In strength of material, the Hooke's law is the constitutive equation which relates the stress with the strain. Okay. So now let us discuss about the Hooke's law. Okay, so Hooke's law says that the stress will be directly proportional to strain for a linear elastic material. Okay, so stress will be directly proportional to strain. Okay, and the law holds good up to a certain point, up to a certain limit, that is known as limit of proportionality. So the limit of loading, basically of loading, up to which this relation holds good, is known as limit of proportionality, limit of proportionality, okay, is known as limit of proportionality. Now, as we have different types of stresses and different types of strain, okay, so now let us correlate them. Okay, so if there is longitudinal stress sigma, so sigma will be directly proportional to the longitudinal strain. Okay, and as soon as you remove the proportionality in this equation, in this relation, then you will be getting a constant of proportionality, and that is Young's modulus. So E is the Young's modulus, of the material. Okay, and as strain is ratio of two similar dimensions, hence strain is a dimensionless quantity, whereas stress has dimension, hence the dimensions, or you can say the standard unit for the Young's modulus or any constant of proportionality will be same as that of the stress. Okay, so this is dimensionless, okay, and this has a dimension. Okay, hence the dimension of this modulus will be same as that of the stress. Okay. Now, the second one, that is the shear stress. So, shear stress will be directly proportional to shear strain. Okay. So, on removing the constant of on removing the proportionality sign, we will be having a constant, that is G. Okay. So, tau will be equal to G into phi. G is known as shear modulus, or you can call it modulus of rigidity, Okay, this will also be having same dimension, Newton per mm square. Now, let us consider a different situation where a component or an element, you can say an element, is subjected to stresses from all the dimensions, okay, and the stress is a normal stress. Okay, then you will observe that there is a change in volume. Okay, there is a change in volume here also. In this case also, it is possible like this. If all the stresses are tensile, then also this is possible. Okay, so associated with this stress, there will be a change in volume. Okay, there will be a change in volume. This is stresses which is acting normal to the cubical element in all the direction is known as bulk stress. This is bulk stress. Okay, so this is a separate category of stress which is generally important in case of analyzing a fluid. Okay, so in strength of material and in machine design, we won't be needing this stress. Okay, so bulk stress will be directly proportional to volumetric strain, because due to this stress there will be a change in volume. So, this will be directly proportional to volumetric strain. Okay. So, here we can write the sigma n is directly proportional to epsilon sigma n, let us say sigma n b. Okay, sigma n b, b stands for the bulk. Okay, sigma n b. So, sigma n b will be directly proportional to epsilon v. Okay. So, on removing the proportionality sign, we will be having sigma n b is equal to k into epsilon v. So, k is the bulk modulus, Okay. It is also in Newton per meter square. So, these are the three elastic constants, Young's modulus, or you can also call it modulus of elasticity. Okay. This is the modulus of rigidity and this is the bulk modulus. Okay. Now, previously we have discussed that if there is a load acting in the member, that may be a tensile load or that may be a compressive load. So, the tensile load will cause an extension of the rod, that means the length will increase, but the dimension, that is the diameter, will decrease, the thickness will decrease. Also, if you will be applying a compressive load, then the length may decrease, but the cross section area will increase. So, this is the Poisson's effect. So, Poisson's effects gives us a ratio that is known as Poisson's ratio. It is represented by mu. Okay, and mu, for you can say for metals, for most of the metal you will be writing like this, mod of lateral strain, okay, divided by the longitudinal strain. okay, or also you can also call it linear strain, okay, linear strain. Okay. Now, the meaning of this mod is that we will be using the magnitude of strain only. Okay. We won't be considering the sign, that is, if it is a compressive strain, that is there is reduction in the cross section area or reduction in length, then definitely the strain will be negative. Then we won't be considering the negative sign, we will consider only the value of the strain. So, here we will be considering in this equation, the meaning of this equation is that we will be considering only the magnitude of the strain, not the sign. Okay. So, this means only magnitude, it means only the magnitude, not the sign, okay, not the sign. Okay. So, here if you want to write the standard formula for the Poisson's ratio, then it will be minus lateral strain, okay, divided by longitudinal strain. Okay. And in most of the materials, the longitudinal strain will be opposite to the lateral strain in the direction. Hence, this negative sign is showing that the lateral and longitudinal strain are generally opposite to each other. If this is increasing, that is, if this is positive, this will be negative. Okay, if this is positive, this will be negative. Hence, the negative sign will come out of the equation, and this negative multiplied by this negative over here will give you a positive value. So, from this equation mu will be positive, okay, for metals. Now, if the longitudinal strain and the lateral strain both become positive, then the Poisson's ratio will be negative. Okay. So, if mu is negative, that means the lateral and the longitudinal strain will become positive, that means the length is also increasing and the thickness is also increasing. So, in such case the mu will be negative, and such materials are known as auxetic material. Now, here we have loading along one direction only. So, in these types of stresses, loading is along one direction. Now, if the loading is along three directions, okay, then we will be using the generalized Hooke's law. Okay, and this equation will be very useful for the theory of failures. Okay. You will see the use of this equation in the theory of failures as well. Now, if you have an element like this, which is subjected to three stresses along the three directions, let us say this is sigma x, this is sigma x, this is sigma y, this is sigma z. Okay. The Young's modulus of material is E and the Poisson's ratio is mu. Okay. Then the strain can be written as epsilon x, epsilon y and epsilon z. Okay. So, epsilon x is the strain along the x direction, epsilon y is the strain along the y direction, and epsilon z is the strain along the z direction, and these are the strain along the direction of stresses. Now, here you can see this stress, that is sigma x, will try to increase the length of the element along the x direction and reduce the dimensions along the remaining direction, but the remaining stresses will try to change the lateral direction while it is being loaded along the x direction. So, the combined effect will give you the result as epsilon x equal to sigma x by E minus mu into sigma y by E minus mu into sigma z by E. Similarly, epsilon y will be equal to sigma y by E minus mu into sigma z by E minus mu into sigma x by E. Epsilon z will be sigma z by E minus mu into sigma x by E minus mu into sigma y by E. Okay. This will be the strains along these three direction, and adding up these three strains will be having the volumetric strain. So, epsilon V, that is the volumetric strain, will be epsilon x plus epsilon y plus epsilon z. Okay. So, from this equation, on adding up these equation, you will be having sigma x by E, okay, plus sigma y by E plus sigma z by E, okay, minus 2 mu into sigma x by E plus sigma y by E plus sigma z by E. Okay. So, you can take this as common. So, this will become sigma x plus sigma y, sigma x by E plus sigma y by E plus sigma z by E, okay, multiplied by 1 minus 2 mu, 1 minus 2 mu. Okay. Now, if a material is incompressible, okay, if a material is incompressible, then the volumetric strain must be 0. So, epsilon V will be equal to 0. So, on solving the above equation, you will be having value of mu as 1 by 2. So, mu equal to 1 by 2 signifies incompressible material. Also, for perfectly plastic material, okay, mu will be equal to 1 by 2, or you can write 0.5. Okay. So, this was the brief information about the simple stresses and strain. Now, in most of the cases, a component will be loaded along 1, 2 or 3 directions. So, in that situation, different stresses will be there, and that state of stress is known as complex state of stress. Okay. So, now we will discuss complex stresses and strain. Okay. So, when a component is being loaded only about one direction, then it is known as uniaxial loading. If it is being loaded about 2 directions, then it is known as 2-dimensional loading, and if it is being loaded along all 3 directions, then it is known as 3-dimensional loading. Okay. Now, in most of the problem that we will see in our gate examination, we will be having 2-dimensional, that is biaxial loading will be there in our gate examination. Few problems will also be there from triaxial loading. In subject of machine design, the biaxial state of stress is very important for proper understanding. So, this discussion will be very important. Okay. Now, in complex state of stress, first of all, let us discuss 2-dimensional stresses. Okay. 2-dimensional stress. So, in 2-dimensional stresses, you will be having a stress only along 2 dimensions like this. Now, here the element may carry a stress, that is shear stress, along with the normal stresses. Okay. So, here we will be having a shear stress like this. Okay. Now, as this is x direction, this is y direction, this particular plane is x plane, this is x plane, and this particular plane is y plane. Okay. So, sigma y can also written as tau yy, that is the stress acting on the y plane in the y direction. Okay. And this can be written as tau xx, that is the stress acting in x plane in x direction. This x mean the x plane in x direction. So, the first letter will be for the plane and the second letter will be for the direction. Okay. So, this will be tau xy. So, this is the stress acting in x plane, but in y direction. This is a negative y direction. Okay. So, this shear stress will be tau yx, that means shear stress in y plane, but in x direction. This is negative x direction, this is positive x direction. Okay. And these two stresses are equal in magnitude. Okay. Tau xy is equal to mod of tau yx. Now, if there is a plane, like this, this is a plane, okay, at an angle of theta degree, then we can write the value of normal stress and shear stress on the oblique plane, okay. So the normal stress, this is the oblique plane like this, this is tau xy, this is tau xy, this is sigma x, this is sigma y, this is tau xy, this is tau yx, okay. Here this is in this direction and this is in this direction, okay. This is theta. Now, so the normal stress is given by this equation, okay. This is sigma n or sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta, okay. And the shear stress at this oblique plane, that is tau, or you can also write it tau theta, that means the shear stress at the oblique plane inclined at an angle of theta, tau theta, will be equal to minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. This will be normal stress on any oblique plane, and this will be the shear stress on the oblique plane, okay. So this will be the normal stress sigma n, and this will be the shear stress tau, okay. Now let us see the principal stress and principal strain. So as we can see that in any oblique plane we will be having two stresses, that is normal stresses and the shear stress, okay. So normal stress and shear stress will be there in any oblique plane. So the plane at which the shear stress is 0, that means the plane in which there is no shear stress, such a plane is known as a principal plane, okay. So let us discuss about the principal plane. So principal plane is a plane, it is a plane at which shear stress is 0, at which shear stress is 0, okay. So tau will be 0 at this particular plane. Now as tau theta, or you can say tau, is equal to 0 for a principal plane, then putting the value of tau as 0 in that equation, you can have the value of principal plane. Now principal plane, the location of principal plane is represented by theta p, where p stands for principal, okay. So theta p will be equal to half of tan inverse 2 tau xy divided by sigma x minus sigma y, okay. Now in this plane there will be a normal stress only, okay, because the shear stress is 0, hence the only stress which will be there in the principal plane is the normal stress, okay. So the normal stress acting on the principal plane is known as the principal stress, okay. So principal stress is nothing but the value of normal stress on the principal plane, okay. So principal stress, that is normal stress acting on the principal plane, normal stress acting on principal plane, okay. Now if a loading is 3-dimensional loading, then there will be 3 mutually perpendicular principal planes, okay. If the loading is 3-dimensional, then the principal plane will be 3. In 2-dimensional loading also you will be having 3 principal planes, okay. Now what is the situation if there is a 3-dimensional loading like this, okay, like this, if there is 3-dimensional loading sigma x, sigma y, okay, sigma z, okay, sigma z, this is sigma x, sigma y, and all the planes carries shear stresses, okay, they are also carrying shear stresses like this, Okay. So, all these stresses are shear stresses. Now, if I will be eliminating all the shear stresses, if there is no shear stresses, only stress acting on this plane is sigma x, stress acting on this plane is sigma y, that is y plane is sigma y, and in z plane the only stress which is acting is sigma z. Now, if I ask you what are the principal stresses, then your answer will be sigma x, sigma y and sigma z are the principal stresses, because here you can clearly see that in these planes there is no shear stress, whereas in the previous example, in this example you will see that there are shear stresses acting on the x, y and z planes. Okay, so they can never be a principal plane. In this state of stress there will be principal planes, there will be principal stresses, but these are not definitely the principal planes. But in this example, these three planes carries no shear stress, hence these three planes are the principal planes, and the normal stress acting on these planes, that is sigma x, sigma y and sigma z, are the principal stresses. Okay. Now, in biaxial loading as well as in triaxial loading, you will be having three principal stresses. Now, why I am saying so, as the loading is only in two directions, then there should be only two principal stresses, right? But this is not like that. In biaxial state of stress, there will be two situations, that is plane stress condition and plane strain condition, and majorly we will be considering plane stress condition. What is that? Let us understand. Okay. So, if a component is being loaded only along two direction such that the stress along the third direction can be neglected, then the situation is known as plane stress situation. Whereas, if a component is being loaded along two directions such that the strain along the third direction can be neglected, then it is known as a plane strain condition. It is very simple to understand. Okay. Let us see a case of a disc. Okay. Let us see case of a disc or case of a thin pressure vessel. Let us take a thin pressure vessel. Okay. This is a elemental portion of the shell metal. Now, due to the pressure there will be stresses along this direction and this direction. Now, if you see the side view, okay, this is the stress, that is the stress acting along this x direction, this is stress along the y direction, and this is sigma y, basically this is sigma y. Now, in this direction, that is z direction, okay, there will be no stress. So, sigma z is 0. Okay. So, here if this is a thin pressure vessel, okay, if this is a thin pressure vessel, you will see that the stress along the third direction is 0. So, here there will be some strain in the third direction, because as these two stresses are acting on the element, then from this equation epsilon z will not be 0, as sigma z is 0, but sigma x and sigma y's are non-zero values, hence epsilon z will be there, that is strain along z direction will be there. So, this kind of situation where the stress, if in a biaxial loading, write down, if in a biaxial loading stress along third axis, or you can say direction, is 0, but strain is non-zero, strain is not 0. So, such state of stress is called plane stress condition. So, it is nothing but a biaxial state of stress. Okay. Also, if it is a plane strain condition, then what will be the situation? Let us assume a cube, okay, and here is this stress. Let us say this is sigma x and this is sigma y. They may be tensile, they may be compressive. Here I am taking compressive. Now, this face is fixed. Okay, this face is fixed. So, let us see the view like this. From the front view, you can see this is fixed like this. Okay. So, here if there are stresses acting on the body, this is sigma x, this is sigma y, and there will be strains associated with these stresses sigma x and sigma y. But the thing is, as the material can deform along this direction, that is, if this is z direction, then the material can also deform about z direction, but the deformation is being restricted by fixing the member between two rigid walls. Hence, due to this restriction, a stress will definitely induce, a stress will be there, okay, sigma z will be there. So, sigma z will be there due to the restriction in the deformation. If it is free to expand in z direction, then there will be no such stress in the z direction. Now, as this deformation z direction has been restricted, stress will induce, but as the restriction is there, the member is not free to expand or contract in z direction. So, strain along z direction is not possible. So, in such case you can see that there is a stress in the third direction, but the strain in third direction, that is z direction, is not possible. Hence, this is a condition of plane strain. Plane strain. Plane strain. So, in plane strain situation, the strain along third direction is 0. The strain along third direction is 0, okay, but stress need not to be 0. Okay. So, stress can be there, but strain will definitely 0 at the third direction. So, this is condition of plane strain. Now, in majority of cases in our problems of machine design, we will be discussing about the plane stress condition. Okay, we won't be discussing about plane strain condition. The majority of cases will involve the plane stress condition. Okay, now let us see the analysis of a plane stress condition. And in plane stress condition, I will be telling you that what is the proper approach. I will be telling the approach of Mohr circle, as using this equation. You can find the normal stresses, okay, as well as the shear stresses in any biaxial loading. For triaxial loading, I will be telling you what is the proper approach, okay, what is the fundamental concept involving the triaxial loading, and also I will be telling you the Mohr circle for the 3-dimensional stresses. Okay. Now, here from this equation you can find out the location of principal plane, and using this value of theta in those equations you can get the value of principal stresses. Okay. And the principal stresses are, okay, sigma 1 and sigma 2, okay, sigma 1 and sigma 2, okay. So, if you have a state of stress like this, so this is the 2-dimensional state of stress, sigma x, sigma y, okay, this is tau xy, this is tau yx. Okay. Now, here your element, you have, or you can say you have drawn the element in a 2-dimensional space, that is with respect to x and y axis. So, it is basically a 2-dimensional view of your element. Okay. And as I have told you about the 3-dimensional state of stress, you can consider it like this. Okay. This is like this. This is sigma x. Okay. This is sigma y. This is sigma y. Okay. And here we have the shear stress. This is tau xy. Okay. This is tau yx. Okay. This is again tau yx. Okay. And here will also be have a shear stress in this surface. Okay. Like this. Now, the stress along the third direction, that is z direction, is equal to 0. So, here we have 3 axes. This is the x direction, this is the y direction, okay, and this is the z direction. and you have drawn the element in xy plane only. Okay. So, sigma 1 and sigma 2 are the stresses or the principal stresses in the xy plane, okay, in the xy plane. Now, for the 3-dimensional state of stress, okay, as you have considered a plane stress condition, so the stress along the third direction will be 0. So, now the stresses along third directions are also taken into the consideration. Okay. Now, if you write the formula, then you will be getting this the principal stresses in xy planes. So, sigma 1 and sigma 2 can be written as sigma x plus sigma y by 2 plus minus root over sigma x minus sigma y by 2 whole square plus tau xy square. Okay. This will be the principal stress. This will be the principal stress. Okay. And associated to the 3 planes, that is x, y, y, z and z plane, there will be 3 principal stresses, sigma 1, sigma 2 and sigma 3. Okay. So, 3 mutually perpendicular principal stresses will be there. Okay. Sigma 1 is the representation of the maximum principal stress, or you can say major principal stress, Sigma 3 is the representation of minimum principal stress or minor principal stress, and sigma 2 is the intermediate principal stress. Okay. And if this is the state of stress, then you can write down the formula for the maximum shear stress in xy plane. So, maximum shear stress in this particular plane will be tau max is equal to root over sigma x minus sigma y by 2 whole square plus tau xy square. This will be the maximum shear stress. Now, this is the maximum shear stress in this plane, in given plane. Hence, this is also known as in plane tau max. That is in plane maximum shear stress. So, for the given plane, that is xy plane, this will be the maximum shear stress. If you will be taking the yz plane, then the value of maximum shear stress will differ from this value, and also in case of zx plane, the value will be different. Now, among these 3 values, that is the shear stress in xy plane, yz plane and zx plane, there will be a greatest value of the shear stress, and that is known as the absolute tau max, that is the greatest shear stress present in the element. Okay. So, let us talk about the absolute tau max, and it will be also the part of discussion in the Mohr circle for 3-dimensional state of stress. Okay. So, you can apply the same formula for the different planes. Okay. So, if you write the same formula in yz plane, okay, in yz plane, you will be applying the same formula. Okay. Hence, this will be tau max is equal to root over sigma y minus sigma z by 2 whole square plus tau y z square. Okay. You will be having another value. Let us say this is tau max 1, this is tau max 2. Then for zx plane, you will be having tau max 3 as equal to root over sigma z minus sigma x by 2 whole square plus tau x z or tau zx square. Okay. So, this is the third stress, that is the shear stress acting in the zx plane. So, with respect to 3 planes, we have 3 in plane tau max. So, this is shear stress or the maximum shear stress in yz plane. So, this is in plane, okay, in plane tau max. This is also an in plane tau max. Now, if the situation is such that sigma max 2 is greater than tau max 2 is greater than tau max 1, okay, and it is greater than tau max 3. If let us consider such a situation, then this value which is greatest among the value of maximum shear stresses is known as the absolute maximum or absolute tau max, or you can also write it tau max ABS. Okay. So, this is the absolute tau max. So, this is the greatest shear stress present in that element, and if the design is based on the shear, that means a particular member is weak in shear and design is to be done on the basis of maximum shear stress, then we will be using the value of absolute tau max for the designing. Okay. So, this is the concept of in-plane tau max and the absolute tau max, and the concept of principal stress is very clear. Okay, is very clear. Now, sigma 1, sigma 2, sigma 3 are the principal stresses, and the value of the principal stresses can be considered by two approaches, and those approaches will be the part of next lecture. Okay, thank you.